And while my colleagues developed the form finding method to shape the geometry of a structure, they were actually lacking the strategy to design the topology of it. I'll first describe the method. So that's called thrust network analysis, developed by Philip Bloch in his PhD, and further by Matthias Rippmann. What you can see here at the top is the final shape, the form-found shape that's funicular, so that can stand in pure compression. Why do we care? Because that means you can make it out of low carbon materials like earth, masonry. You can make a very efficient thin concrete shell out of it. So it has very interesting structural properties. And so the geometry of this funicular shape is defined by two things, the two bottom diagrams. So this one, which is like a top view of a force flow, the path of the forces throughout the structure, which is a form diagram, and a bottom one, which is a reciprocal one that shows the distribution of forces within the structure. So if you have a look at a couple of features here, help with a color map, you can see that the higher forces here along that red boundary, the edge, is shown by is related to the equilibrium of this part in red. So we have a method to describe the form, but what's very important in a structure, whether you talk about masonry vaults and load paths like this, or a simple steel truss, it's so the load path, the connectivity of structure that allows you to bring the loads, so the forces, all the way down to the supports and the foundations. And what you can see here, so for this nice array of shapes, so they all have somehow a circular boundary. They are still quite different. Some of them have straight creases like this. We have this regular grid. This one has one free edge. This one has three. This one has inner openings. What's very essential is actually to draw out the diagram first, so the topology of a mesh or the network. Because if you were to take that regular grid and try to apply it here by just trimming it, you wouldn't be able to find a relevant shape that can carry the loads nicely here, mostly around the borders. So that was my mission, to be able to produce such meshes or networks that nicely integrate these features. Creases where you have higher forces that need to be strengthened, but that are primary load-bearing elements. Open edges that are the weaker part of a structure because it's just partially supported, and similar for the openings. And though here I mostly show this maybe abstract, or let's say virtual force flows, you can actually more nicely see it on a physical pattern, so built structures. And here I like to show this couple of projects that have been built and help us understand the changes when it comes to designing and building structures with a complex topology. Here on the left, you can see this regular grid. That's nice because you only get flat panels, so flat quads for the panels in glass that are cheaper, but doesn't take into account the boundary conditions of the support. So you can see here that along the edge it's just been trimmed. So there's not an efficient load path towards the support. You have these awkward elements that need to be detailed with these triangles or pentagons. So here the boundary conditions, the support conditions, and the one not taken into account, which is key when it comes to mechanical efficiency. In the middle, you can see that funnel where you have a transition between the horizontal part and the vertical part. And you can see that the two areas where you have this complex transition have been patched between regular quads, like here at the bottom, a triangulation here, and then a gradual transition. You can see here that maybe most nodes have 6 adjacent beams. This one has something like 8. So it's been based on the skills of a designer without any support of an efficient tool to design it. And that's how you get this um, structure that's made of patch of different elements and don't have really full control, an efficient control or way to explore the design space. And the last one on the right, so you can see here you have a quite a complex connectivity that's quite variable with small openings, larger ones, and mostly it lacks hierarchy. And when it comes to structural design, we like to have a hierarchy to understand how things behave, or how do we build them from the main elements to the more secondary ones, which ones carry most of forces, which ones are more for um, local stability. So these three examples actually show that it's not easy to actually nail this. But if we look around, we have amazing examples in nature, so that are familiar to us. You can, if you have a look at the properties that they have, starting with the honeycomb, they have this modularity. So even for a complex structure, if you zoom in, you only have these hexagons that are quite simple. But when you combine these modules, you can produce more complex shapes. In the middle, you have this, so like a regular pattern for so zebra stripes that you can see here. But when you have a transition here in the middle, above the leg of a zebra, you can see that you have this kind of singularity. So where you have this, you change from a regular area to a regular one to get a smooth transition um, and deal with the complexity of shape. And the last one on the right, you can see on the leaf that you have some hierarchy in between the different elements. So the thicker ones that are also load-bearing that carry um, and that's have and that are more like the primary elements, and then the smaller ones in white that are more secondary. So it's not because overall the pattern looks quite uniform that every element should be different. Here you have this clear hierarchy between some of them. That's actually what we find in maybe the most beautiful and therefore elegant, efficient and affordable structures. So you can see the British Museum by Forst and Arup on the left. You can see that despite its nice, complex shape and curvature, it's made of these regular triangles of modules. In the middle, you have the Pierluigi Nervi rib floor. So that's just a rib concrete floor in a factory, but the design of it, the pattern of the rib has been informed by the boundary conditions. So here in that case, the position of the columns. So that's why you can see these poles with the beams and in array, in a polar array that radiate to the column. So they actually bring the forces, so the loads toward these supports. That's why you can see these irregular elements. And here, so that's the King's College Chapel in Cambridge, in the UK. And you can see that in this fan vault, here you have this array of elements that also bring elements towards the columns. But more particularly, what you can see here, you have these regular ribs, and here you have these thicker ones here. And they're not necessarily meant to carry higher forces eventually once it's built, but it's meant to be assembled first. So you actually build first a centering, so a set of wooden elements. You can put the stone blocks, the voussoirs that make the arch. So a light arch supported by this centering. Then you can span in between. So there's an hierarchy in construction, which we usually don't see unless if you look for photos in all the books or online. But that's a key thing to think about. What's the construction sequence? So these are the kind of changes. Oops, sorry, I went too fast. So these are the changes we're facing. So that show. Sorry about this. That show that it's not just about structural efficiency, it's also about fabrication. So fabrication regularity, assembly sequencing. It's very much a multi-objective task when it comes to the engineering and the design of a structure. But if we simplify the problem for now, assuming that when we design a structure, it's just about mechanical efficiency, using less material, less carbon, and we revisit the British Museum, so the grid shell here, with a tool that I used in my PhD for study. Here you can see 4 designs that have roughly the same number of elements, so similar number of nodes to assemble, so similar fabrication complexity. It has exactly the same shape that's been defined by the researcher Chris Williams, who analytically wrote the equation for it. But they only differ by the irregularities, so the singularities that you can see in pink, that completely reorient the flow of elements, the flow of beams, and therefore the flow of forces. If you zoom in, you can see that all the regular nodes have 4 beams coming together, but this one has 5, as highlighted by the black line. This one has 6. These 2 have 5. This one has, as you can see at the bottom, is like this pole, like um, the rib concrete floor that you saw just before. And so what's interesting is that with a similar number of elements, similar geometry, if you try to optimize them just for mechanical efficiency, you can see that depending on how you orient the pattern through its topology, you can go from you can make the design better or worse. So you almost have a ratio of 2 when it comes to this. So when you think about it, it's just by choosing the topology, you can double the amount of material that you need to use. So in this abstract study, you can see how important it is. And so that's what set out my PhD topic. How do we actually explore the design space of the topology of patterns? I just showed 4 examples before this fairly simple shape, so a rectangle and a circle in the middle. But you can see here just a subset of other possibilities. The differences are highlighted by these pink dots, the singularities, and shows that it's quite a complex design space because of its nature. So it's not like playing in Rhino and Grasshopper. We can play with sliders and change the shape. Here, because it's not about geometry, it's about the combinatorics, the topology of a pattern. The complexity of design space increases exponentially. So we actually need methods and tools to explore it. And that's what I set out to do during my PhD, which was to define rules. So in a generative design approach, to be able to modify a pattern and explore its performance. So roughly speaking, if you have a look at this base design, this starting design on the left, you can see this blue arrow that's gonna travel through the main line. So in red for the boundary and in black for the inner edges, and collapse some of the elements and add some new elements. In that way, you can produce a couple of patterns based on your intuition and evaluate their performance. So here you can see a different set of metrics, so objectives. As I said, structural design is a multi-objective task or challenge. And so the first ones are about mechanics, so maximum deflection of a structure, the stresses in it, the buckling or the stability of it. And the other ones are more related to fabrication. So how curved or skewed are your panels, and when you want to make a follow structure, you want to simplify this so they look like flat squares, and also the variation in length of the elements. So just a couple of metrics that out of different ones that are always project specific. So it's not about saying these are the absolute metrics, it's about providing a tool for the designers to actually combine them or insert them into their own workflow and explore that design space. And you can see here there's no right or wrong answer. There's just a set of designs that produce some better than others for some metrics, but it's always up to the designer to choose depending on the specific project constraints that are always evolving during the design process. And but that said, I'm trying to, because it's a very complex design space. Just before, I was actually showing design that are intuitively produced with my generative method. But the aim is to make it accessible to people who don't have to spend a couple of years studying this. So the aim is to be able to combine that open-ended design tool into something that a problem that the designer can formulate. So here, something that's work in progress. So it's not there yet, but the goal being to formulate it as a problem, a design problem. That's whether about minimizing the load path, which relates to structural efficiency under some constraints related to fabrication, assembly, etc., or combining a set of objectives that have different weights that you can vary depending on your requirements. And the aim is to be able to start from just the most simple mesh you can see, which is just a square, like a base square like this, and let an algorithm run, search the design space, informed by the target being mapping that boundary, trying to be structurally efficient, not having too long edges, and obtain such a topology like this that can evolve from something that's completely agnostic to a final design, that base square, getting something with an interesting density, interesting singularities like this at the corner that nicely map while you have this concave area. So that's work in progress. That to be able to make, say, almost off-the-shelf but transparent design tools that can be integrated into existing workflows. But before this, before trying to search through the entire design space, there's already a lot of intuition that we can use as designers, so architects, engineers, and I like to show it on this example that based on a strategy that I developed. Imagine that you have to design some kind of a pillow shape for a grid shell, like some nice courtyard cover or something like this. I would personally like that design because it has this regular grid that's quite easy to build, not too many complex elements, but it doesn't take into account the support conditions, assuming that you have to your support only at the corners and you have to take a point load in the middle. That's also why I like that design that's more complex to fabricate, but there's these nice poles that bring the loads towards the supports. I also like that one with the pole in the middle because it's a nice way to spread the loads in all directions in an efficient way. So then what do we do now? Do we go for this one, or this one? So they're all the best for what they've been drawn for, but they're actually, they don't really work when it comes to complying with these multiple objectives. So but I developed a strategy to capture the main topological features of these input designs based on my intuition and get some hybrids, so topological hybrids that can be relevant candidates for the designer. So if you just zoom in on that one, for instance, what's interesting is that it captures the regular grid from this one. It also has the poles at the corners from this one. And if you go through all of them, you can see that they have different degrees of similarities and differences with the input designs. And more interestingly, is that the performance actually follows the topology. So indeed, if you evaluate for these three metrics, so edge length regularity, this one, so it's minimized, so it's the best. So this one is the most interesting one. When you have a look at the energy, so which relates to the amount of material that you need to use, like this one for point load, so EP. This one is the best because it's a minimum one. And then all of the other ones will give you a different trade-off. And more specifically, the one in the middle actually gives you, it's not the best for any of these objectives because it's hybrid, but it's quite a balanced set of performances. Maybe that's not the one you want as a designer, and maybe another one is different, but at least by just starting from these three input designs and combining combining the topology of them, you can get um, um, trade-offs for performance. Now let's try to, so I'm a big fan of shells, vaults, and grid shells, but I'm also interested in applications for more regular building components. So the floors that we have in our space, and more particularly rib floors for larger spans, so which are common, but there's usually two strategies. Maybe a less common one, but you can still find is the one that we saw before. So like what Pierluigi Nervi did and a couple of other ones is to follow the force flow, the natural force flow that the structure would like. And so you have a very small amount of material that you need. But it's tricky to produce because you can see, despite the nice regularity of support conditions, most elements are different. So it's not relevant for, say, modular construction where you would like to have a set of, let's say, maybe complex, but a small set of elements that you use for your formwork to cast concrete. And on the other hand, that's more popular, the waffle floors, where it's perfect for modular construction. You have a repetition of all the elements, so you can invest in a more high-end prefab setup. But it doesn't follow the force flow of support conditions at all. In that you can see that example where in here what you would have a nice pole where all the beams come together. Here you need to have this big patch for local reinforcement. So you avoid like in a very practical manner the column to punch through the floor. So in terms of structural efficiency, that's not the best one. And because I'm interested in hybrid solutions and compromises, trade-offs, the question is that I'd ask myself is, can we find something that's between a solution where everything is custom and something where you only have one module, one unique module that you repeat, and try to be efficient in terms of material consumption in the final state of the structure, but also the production state when it comes to the formwork, these molds that you use to cast concrete on. So again, just based on the intuition to start off, that's like recent work. Instead of just one module like this, like the gray block that we saw before, I forgot about having 6 modules with poles at the corners for some and exploring all the different combinations. You can see that you have that way a kit or a catalog of 6 different modules that you can orient in different ways. And the question is, with this, so only 6 modules, so we can be quite efficient when it comes to mass production. It's not mass customization, but mass production elements. And can we combine them a bit like a puzzle or a Tetris puzzle and apply to different design with different boundary conditions? It's quite easy when your floor, your boundary conditions look like this that are quite regular. But what if we have something like this, which is on the right? So like this L-shaped floor seen from a top view, a couple of columns of these bigger dots and a wall around here. Here you can see, then the question becomes, how do we put these, how do we choose and where do we put these blocks like pixels to fill in the space for that floor? What you can see here, the small crosses are information about what would be the natural force flow when do a mechanical analysis. So the answer would be something like this, where everything is custom. But again, the question is, let's try to fit um, that force flow, but with just the constraint that we have. So like this inventory constraint approach with these 6 modules. So it's nice to benchmark, and usually we benchmark against a classic, but usually not the best solution, so the regular grid. If we measure the elastic energy, again, that's like the load path in some way. It's a measure of the structural efficiency of the material consumption of your structure. That's what we have for the regular grid. If we follow the crosses that we had just before, where everything is custom, you get this stress pattern, and that's what you have. So you can see that it's about 35% more efficient than the regular grid. And then I was trying to explore and try to optimize the combinatorial problem of where do I allocate these blocks. It's not a simple problem because there's exponential complexity. So I tried a couple of algorithms, but eventually combining intuition and optimization, managed to get something like this, a design like this one, which I render here on the right side, which I was quite pleased with. And you think about it, um, it's 30% better than just the single module design by allowing only 3 different kinds of modules. It's only 10% worse of this one, the theoretical optimal design. The question is, can we do better? Can we get closer towards the left of that space? Well, the question lies in can we get better design algorithms, but also can we find another catalog set of modules with more options that will allow us to have more design freedom and get closer to like the theoretical optimal. Doesn't make too much sense to go for bigger catalog. That's too big. A bigger catalog would add possibilities, but if you have to deal with 10 blocks, it increases the complexity of the design space that you have to explore. It also increases the complexity of the cost of the number of modules that you have to produce. So it's a trade-off between mostly here with the key parameter, which is the number of modules that you have in a catalog. But with that approach, what's interesting is that you can make very expensive, fancy, but reusable modes for formwork that you could reuse. So you don't have to waste them once the structure is cast because it's a single use. More ambitiously, if you actually manage to get a connection that allow not the demolition but the construction of the modules, you'll be able to disassemble them and repair them, store them, and reuse them in a different configuration in some way. So contributing that way to a circular economy. And in that sense, for construction, it starts by having some level of rationality. So not something that's too simple, but some level of rationality as to what you produce and making sure they're compatible down the line when you reuse them. And that leads me to a project I want to show. That's when I was in Cambridge as a postdoc researcher. We only have very shallow ribs, and it's not flat, it's curved, but the aim was again to address how can we reduce the environmental impact of our built environment. So in that case, again, building floors of concrete blocks. Why vaulted floors? Because they can be extremely thin, so funicular structures, as we saw at the beginning. So impure compression, which is the most efficient way to use a material like concrete, more particularly. And how can we actually make sure we don't have to destroy it, but we can actually disassemble it? So that's a prototype that we built. If I try to convert it, let's say it's 200 square feet. You have these 9 modules that have been produced before. in prefab. During COVID, prefab meant just behind in the setup. We didn't get to build this outside the lab, but we got to use them before, assemble afterwards, and and um, and try to obtain a solution, let's say an option alternative with try to minimize the embodied carbon of the structure. And when we crunch the numbers, so if we benchmark it against a regular flat slab, which is the worst solution you could think of, you can think of worse, but that's not the best solution. We managed to reduce the embodied carbon by 60% and the mass by 70%. And the mass matters too, because eventually that's what the columns, the lower floors and foundations have to carry. So we check these two metrics mostly, but to do more thorough life cycle analysis, we need to take into account other aspects, not just embodied carbon, but that put us in the right track. So we're quite happy with it. Again, it's meant to be not just a roof, but a floor. And we didn't have to reinvent the wheel, so we use this off-the-shelf level floor, which is popular mostly for offices, maybe less so for housing, but um, that came in handy. That in between space, you could imagine having the services, so conduits, pipes running through. There's of course quite a few problems to solve, but we managed to produce that structure. And I want to show you how, in that case, to build this circular structure, topology was a key aspect as well. So to produce them, we actually use robotic shotcrete or concrete spraying with glass fiber reinforcement. That's why it has this look. Yeah, what was key was the path planning. So you can see we're spraying in different directions. You can see it from the kind of strips. To optimize the structure, it doesn't have the same thickness everywhere. So that's why you have these kind of ripples. And then we also added these very shallow rips along the main load path. So all of this with in mind the structural efficiency, and then related to the trajectory of the robot, and making these complex elements so doubly curved variable thickness with ribs was made possible thanks to digital fabrication in that case to achieve something with something closer to the accuracy we wanted. That was for fabrication. Okay, too fast. Then for assembly, so here we had some kind of scaffold or platform for safety and accessibility, but eventually we just put these 9 modules on these telescopic props. And then what we did, we put them a bit higher than the final position. And then we were just lowering down, let me replay this, lowering down the props so until the gaps between the modules would close, and until the props, like the one you can see at the back on the left, will actually be loose. And that's when we went from modules to a set of elements that work in shell action and are all thrusting against each other. What was important here was, and it relates to topology and how we designed the different blocks, was the assembly sequence. But I will demonstrate on this assembly sequence. We are aiming for dry joints, a bit like with the shear keys like you have for some bridges, to be so dry joints, no mortar or anything, to be able to disassemble them. And here we just had to reverse slow. So the high res videos doesn't go through. Okay. So here we had to put the telescopic props back, push up by a couple of inches, and then remove the elements. So first the oculus, like the central piece, then take care of one side of the boundary, etc. So that shows how we in reverse sequence how we assemble it. That was the easiest part of the project. and thanks to the detailing that we had, so dry joints to be able to disassemble them, we use them as such. And that's actually what we first did a fabrication, let's say an assembly test at ground level to be able to make some corrections that we had to do because we were within, let's say half an inch in terms of precision, so we had to make corrections. Then we did the assembly test on the columns to showcase what it would look like as a prototype. Then we brought it back down to be able to assess how the structure behaves by loading it here in that case in the middle to see how it behaves, because it's not just a concrete shell, it's made of these module segments with dry joints, so it's closer to masonry behavior. So I wanted to know it was going to fail, and you can see that this is starting to go up while this was pushing in, and then you have this like asymmetrical behavior, and then a quite sudden collapse, which is actually not the kind of failure mechanism that we want. So there are things to work on there, but it allowed us to show or to see that these structures can carry loads properly, that they can be used for floors. And when we communicated with people from the industry. So as I said, in that structure, thanks to the design of the joint, we're able to disassemble the pieces and reuse them, putting them back together. But similar as to the rib floor that I showed before, the question we had was, can we actually find a way to make sure that these modules can be used for different configurations? Let's say from a square plane to a rectangular plan, different spans. So that's what Mishnu did during his PhD. He was working with me on this project, and more specifically, he had a look at this. How do we bring in a reconfigurability potential with circular economy in mind? We just looked around in Cambridge, and as we saw before, we saw these fan vaults that are nice because of their symmetry of revolution. And so by changing the proportions, he actually used that to have this hybrid floor that he explored. So a curved structure with these fans close to a support, and then the spandrels of a flat part in the middle that is thicker and allows you to deal with transition between the different funnels. So quite exploratory. There's a small prototype he did, and if we compare things that can be compared, so previous prototype that we did and this one that were made using the same methods, we saw that calculated that the carbon cost of the embodied carbon was 20% higher by changing the shape and the logic to make it reconfigurable. So that's a ballpark number. A couple of things are not necessarily taken into account, but at least it gives an order of magnitude to answer a classic question, which is, should we optimize a structure for its use now and for the next 50 years, or should we make something that's more resilient, that we can disassemble, that we can use for different things, different configurations? And well, in that case, it shows that for our specific structural system, if you allow reconfigurability, but you extend the lifespan of a components by less than 20%, well, that's definitely not worth it. So that means that if you build a floor, it stands for 50 years, reconfigurability allows you to go for 60 years or more, and we can start talking. So that's just a ballpark number to know that that is something that's relevant and an interesting direction to explore. If I connect the two projects that we saw, so spraying these concrete elements out of concrete, and trying to get these rib floors that we saw before. Digital fabrication allowed us to produce these pieces with these ribs. where you could imagine that they start carrying higher forces than the rest of the shell. You can maybe have post-tensioning running through. That was thanks to the rheology of the material. So that was concrete with glass fiber in it. And with the robot, we could actually nicely spray those. So following in that case, optimal lines in red and blue. But that was key. So we have this complex topology. So not necessarily intuitive to know in which order to go through. Because when you spray concrete, you don't want to pause because otherwise you kind of make a mess. So it was an idea of path planning going through or traveling through these edges. I'm going to highlight it on let's say the complementary fabrication technique that I worked on there. That relates to reinforcements. So you've heard of probably of the embodied carbon of reinforced concrete, especially for flat structures that work in bending, so beams, flat plates. What's interesting is that so these structures are over designed, so there's too much material in it, mostly concrete. But concrete only accounts for 60% of that actually. If you have a look on the left side, so you can see the rebars, reinforcement bars made of steel. They actually account for 40% of the embodied carbon. It's not that much in terms of weight, but because of carbon density is way higher, and because of the way we build with these highly rationalized straight elements, so no complex topology there. If you want to reinforce it around a wall like this or a column like this, you just stack or you make it denser with a smaller space there to here. So here on a more exotic material maybe, but there are people exploring the potential of carbon, filament or carbon fiber construction industry. That's a more popular material in the automotive industry. But what we like about it for structural design is that if you use that flexible filament, as you can see at the top right, and you coat it into resin, and then in that case, using a robot to wind around a set of pins, we can produce this complex pattern that you can see in the middle that can come from a structural optimization logic, where you can actually say, where you can actually try to minimize the volume of reinforcement, and you can follow more complex load paths and try to travel through, a bit like spraying concrete for the ribs before, travel through the elements because you want to have nice material, filament material continuity. Then you can produce something as complex as this. Okay, that's a small piece. It's 2 feet long. That's something that could be combined in terms of reinforcement of the ribs before. So using again digital fabrication to be able to produce complex topologies that come from a structural optimization logic to reduce the environmental impact. But it's not, as I mentioned before, it's not just about the material that you have in the structure itself. It's also about how do we get there, especially for spanning structures, more complex structures, and that's called the false work or temporary structures. It takes into account what you can see in this image of the scaffolding for access, the formwork in timber where you can concrete, the centering, masonry, etc. And what you can see in that picture, it's actually the CNIT. So it's a concrete shell back here in Paris. It's the longest span for reinforced concrete structure. And the engineers and the designers actually won the bid because they managed to produce something that was quite economical in terms of false work. And that's actually what you see on the image. So it gives you an idea of what the others offered. And there was an interesting, still an interesting logic in terms of the sequencing of the assembly, starting from the start and going towards the boundaries. And that's philosophy that we use in a couple of projects. I first show some work that Mahan Motamedi did here during his PhD. So we were inspired by Nubian vaulting, which is a strategy to build without formwork. So instead of putting for barrel vault like this cylinder shape, instead of having these let's say vertical arches, you actually tilt them just enough so that there's enough friction between the blocks so that they don't slide. You start from one end, whether it's at the ground level or against a wall, and you just build like this, somehow cantilevering and spanning a free space without using any formwork. So that's neat for like a spherical dome with rings also, so these simple shapes. But what Mahan did was revisiting these structures and how to produce them for more complex boundaries. So starting here just with a square, uh, producing squinches and pendentives that support each other. So you can see it's also done larger scale prototypes, but you can see on this one was the early days producing starting from a corner, spanning out with a small robotic setup, printing a structure that's spanning, not just a vertical structure where you don't need a formwork usually. We also developed some algorithms to deal with more complex shapes with the idea of finding a topology of a set of patches that work. It's not just about finding a set of patches, also about sequence, let's say the growth. So that's what you can see with these like kind of source points from which it radiates. So you're trying to find a logic, a construction logic that might be quite complex, but because it can directly be translated into a toolpath for the 3D printing setup. And that was um, we were able to make these complex topologies printable and buildable. And last project I want to show that was back in Princeton. So it's about again minimizing the construction efforts to make complex structures like vaults or shells more economical. So in that case, tile vaults. In here, you can see you have these three arches. The project was led by Wissam Al-Assali at IE University in Segovia. You can see him here. We had the logic of not building from the outside inward. We do like the concept of a keystone, but it actually makes it more challenging for different reasons. One, it's harder to, when you put the keystone, you need to be sure, you need to have a way to deal with the tolerances. You make the space more cluttered. Here we like to build from these prefab arches from the spine, build outward. It was easier to do. That logic starting from. And a couple of different strategies I'm going to show in a minute. We try to simplify again the construction complexity and cost. So we try to estimate by with mass of force work all these temporary elements that we have to design, assemble, disassemble. So we managed to minimize the mass and the number of connections quite a bit compared to a more classic, let's say, vault or stone vault if you were to put a full centering below. So like with a classic steel scaffold with timber elements on it to be able to know what is the shape like. Another key element, as I just said, you need to be able to know what's the shape like, especially for complex structures. In that case, that came from a form finding logic. So we work with a master vault builder, Salvador Govis Avinos, and we introduce him to augmented reality. And that's what you can see from his point of view, wearing the headset, real speed, and not having to put these temporary elements to know, not to support structure, but just to know what's the shape like, because especially for complex shapes, behavior is very, depends highly on the accuracy of it. And here you could just follow these, work freely without anything cluttering his workspace, and work more efficiently. as well as not having to spend half of his time prior on site assembling the guide work. So that's what it looks like. So we just have these prefab elements that are connected together, and that's across 5 days in total. You produce a support, and then with a materiality technology that tells you the shape, but also can inform you with a assembly sequence. And following our form finding logic that we're able to communicate to Salvador, could actually follow you could actually follow the shape and produce the different parts of the vaults across 4 days. The initial part was a bit slower because of the complexity of the shape. So you have these 3 legs, so you have this singularity, a more complex topology at the start. Then once it's done, it goes faster on the edges because you only have regular elements. So like this part here. And maybe a late comment, but so that was led by Wissam Al-Assali, who's interested in structural crafts. So it's about lasso, grid shells, Catalan vaulting that we just saw, basket weaving, and he's made a piece, an exhibition piece at the Venice Biennale, and in a week or two. So I'm not sure if you've been there, if you're planning to go, but you can find more about this idea of combining technology, design technology, but also structural crafts. I spoke about digital fabrication, robotics, but when it comes to making more complex topology happen, but we also have these more low-tech solutions to be able to produce these beautiful and structures, as you can see from the shadows, not trivial ones, through their geometry, the system, also the pattern that need to be produced. I just end with maybe a couple of takeaways on why structural topology matters. Again, it's about different aspects. Maybe the first one, as an engineer, would be structural efficiency, designing a load path that makes sense, that's as close as possible to the optimal one. Also, planning the construction sequence. So that's also a discrete problem. So how do we put things in the right order to be able to build them with minimum scaffold, centering, support, different sorts. Whether we're talking about vernacular crafts or defab, and also how do we think about technology as a tool for circular construction to be able to adapt structural system of the components that make a structure and reconfigure them for different use for which they've been designed. So that ends my talk, and thank you a lot for your attention. Happy to take questions.
Thank you so much. We have time for 1 or 2 questions. Who would be brave enough to ask?
Thank you for your presentation.
It's not working.
Hello, can you hear me?
Hello?
Yes.
Can you hear us?
I can hear you.
It doesn't sound like it's doing anything.
I can hear you, but it's a bit faint.
Hello.
Yeah.
Sometimes working.
Doesn't sound amplified to me.
I think this is working, but
Yeah, I can hear you.
Very well.
Maybe I have to stand over there.
So now you are speaking with the room mics, and they are actually there. So not at the over there. I think if you speak up, then you will hear us. Okay.
Okay, so it does sound better here. The talk raises a great number of like interesting technical questions about usability, modularity, adaptability, pulse work, you know, how you trade off these various possibilities. You're talking about multi-objective optimization, trade-offs. Maybe more interesting for the students of architecture than all those technical issues is how do you deal with the trade-offs between structural criteria and non-structural criteria? Like when the architect would prefer to use a form that's really suboptimal structurally, or for environmental reasons, you know, in terms of ventilation or daylighting or whatever. What approach do you take? How do you compromise a very well thought out structure ways to accommodate those other things?
Thank you for the question. I think what's useful is to have, let's say, tools that help us search meaningful design spaces, whether it's something where the designs are buildable or efficient, whether we're talking about mechanics or daylight or comfort. Then the challenge is really how do we combine them, and I think it's what I usually have is it's a hierarchy in terms of objectives. Maybe first we want to make sure you want to make sure that your structure is buildable. You have like clean connections that can be produced, and then you try to find something that's more efficient. So you have to identify the key criteria, and that's also how it shapes my design workflows. First, I think it's important to have tools that are compatible. That's also why the methods I've developed for topological design it's not meant to be a solution for everything. It gives you different topologies, but some can be combined with different shape or geometrical design functions. You can evaluate performance for daylight or mechanics and see how it behaves. So I think it's about compatibility, but also having a clear hierarchy between the different objectives. Yeah, that's my main focus. I'm talking about structures, and for those, when it comes to if we think about environmental impact, well, the embodied carbon of structure is the and construction aspect is key. But I think if I were to build a different kind of structure where daylight, when we're talking about facade, daylight is a main problem, where but vertical structure with efficient load-bearing system, usually then daylight will probably come in as the first criteria.
Thank you.
Good question.
Okay, thank you for the lecture. So for some of the earlier stuff that you talked about, like with the rectangles and the circles in the middle and connecting the nodes, and then also your concrete slab structures, I noticed one thing that you said was that a lot of your decisions were kind of based on intuition as well as what the computer told you. So you were placing your nodes and your poles like in the corners or in the centers, and allowing it to make a few variations based on that. But I know, it kind of exists that we can let the computer take over some of those decisions and think more parametrically and like have like thousands and thousands of variations, and eventually one might be the most optimal. But obviously that's not exactly what you chose to do. So I'm wondering kind of what your philosophy is of where do you stop the computer, right? Because we can make these parametric structures and make them really, really optimized, but sometimes that's too complicated, too much data. How do you approach that?
Yeah, thanks. A very important point, and it allows me to clarify this, and that's also what my research has been about, to provide different methods that go from very practical, very intuitive strategy for the designer to something that's maybe not as much digestible by the designer, but that can be read by an algorithm. But definitely what I'm trying to do is to have some level of automation, because there's no point trying to reshare the right slide. Okay, because there's no point in me knowing how to do this. The point is to be able to have as many people tackle the different changes. Okay. So on this slide, these ones were not produced manually. There's a generative algorithm that's deterministic, so it's a straightforward. There's no stochastic process. By saying, okay, in this one, I say that I like the boundaries. I want to have a nice alignment with those. In this one, I want to have the alignment with this curve. In this one, I want to have the pole at the corner. And here I want to have both. So here I only say, I like these geometrical features, surface boundaries, the curve features, the point features, and I get a resulting topology. So as a designer, I only have to think about real, let's say more meaningful objects for the design, and get a result out of it and see which one I like better. For the other one, so this one and this one, it's more based on a graph logic, and the designer can actually, let's say, get their hands dirty, change the topology, making specific changes. So here in that case, from 0 to 1, I delete that strip. So it means that the 4 pink nodes are going to go there. So here, you have to make a decision in terms of the topology and its design. But it's within a couple of clicks, you can get something out. It's quite efficient to produce. And in that one, it's kind of let's be smart as to what are the objectives, the constraints, what's the problem, what's the design problem, and let the algorithm run. So these are these 3 different levels between geometrical features that the designer plays with, changing like the topology of a mesh manually, and then let's say partially manually, and then the algorithm running on its own. So I think it also depends on if you want to get something that's as close to the optimal as possible. If you try to mass produce something, if it's then if you have so many requirements that you can't actually formulate them as objectives because it's part of a bigger discussion with many people involved. So that's why I try to have these different levels, but actually using a similar approach or similar grammar to explore the design space. Sorry for the long answer.
Thank you so much. Thank you, Ruben, again for joining us. It was wonderful to have you. Because we went a little bit over time, I think if there are any follow-up questions, then if it's okay with you, I will let them reach out via email.
Of course, don't hesitate.
Thank you so much again. Yes, I think clapping is in order. I love clapping.